sets. If you know what these are, you might think it is an easy object to think about, but I'm going to make this one very difficult. That's my talent. I just take this easy thing and makes it very difficult. All right, here's my approach. The one thing, before I move on to and begin my style of doing mathematics, I think the most important thing in the mathematics is, of course, this result and algorithm and formula, and those are important things. But I think the way to justify our result is very different from all the other scientific subjects. In mathematics, the way you justify our result is very rigorous. It's all about the chain of reasoning that you think about it. You can't prove the simple result using fundamental theorem of calculus. There will be kind of circular argument. You have to understand what implies what, and then clearly understand the chain of reasoning. So that's why this is difficult to start sets, right? So the first thing I thought about is this basic object. It's not set. It's something that you already know that I don't have to explain. When you were younger, like really children, and when you learn this thing, I think it took a long time to get used to this fundamental basic object, which are numbers. One of the things that you learn in mathematics, right? Numbers. The next thing is a position. I think you learn this one later. Numbers first, quantities, and count the number of apples and things like that. And we learn more system of numbers, and then you move on to the position. First, our idea of the position is a number line. Here it's just location. The number represents where your position is. And after that, you learned more complicated position. That is usually called the vectors. All of you have taken the Calc 3? Is that right? Yeah. In Calc 3, you learn vectors, right? Like position in three-dimensional space. That's the mathematical vectors. So those are the basic object. It takes a long time to go through a lot of experience and examples to get used to that. So we don't have to establish what these are mathematically. Thinking about correct chain of reasoning. As soon as you enter that, you get puzzled. It's very difficult to do that. So we just shoved under the rug that we assume that no problem with this one. All right. The next thing is this collection of these. In mathematics, there's some formal definition about this collection, but that's not what this is. It's just an ordinary, everyday word of a collection. Collection of these. These are these basic objects I'm talking about. Collection kind of involves human action. Here's one apple, you collect one, another one. It seems like that. And that's exactly what I'm implying, and that's something we can definitely understand. So the first example of a collection is a good example. This is a concrete definition. Something called sequences. I think you've encountered sequences a lot in Calc 2, right? Calc 2. So I'm going to give you an example. AN. I think these are usually standard notation for. And photo images of this one will be available. So I wrote down my notes and I printed out, and you have entire thing is there. Still, you can still, and it's better to have your own notes. That's great. But if you feel like you better pay attention to the lecture, not writing down everything, and you will have this entire photo image, so you can easily write down and print it out, just to let you know that's what's going to be available. So AN, I'm going to write down some unfamiliar way of defining AN. I'm not sure if it is a standard definition. This is not equal. This is colon, dot, dot. I'm writing down 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, and so on. So you've seen this dot, 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 right? Whenever you see dot, dot, dots, and you have to ask yourself, do I understand this dot, dot, dot? Okay, what do you say? What do you say? Anybody understood what this dot, dot, dot means? Is that a random thing, or you see a pattern, therefore you understand rest the part of the pattern, So you understand this dot, 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 right? Yeah. There's 1 0 and 2 zeros inserted, right? That's the pattern. So whenever I believe you understand this pattern, I will put you into dot, dot, dot. So I don't have to write down any formula or anything. Right? So this is a sequence. First term is 1, second term is 2, and what about a of 6? What do you think? What is the sixth term? 1? Is that right? So 1. Do you agree? That's the first term, denoted by a subscript 1. This is the second term, denoted by a subscript 2. Whenever there's something that you don't understand, you can frown a little bit. You don't have to raise a hand. I can quickly sense that I need to explain more, something like that. All right? Does that make sense? A1, a subscript 1 is 1, and that's what I mean by this particular example of sequence. So A6 makes sense? It's 1, 2, 3, 4, 5, 6. That's A6. Okay? If I ask you what is the 2014 term, then you probably have to spend some time, but you're not going to count like this, right? But you can probably if I have time, I can calculate that and things like that, right? Right. So already there's a nice question about what could be the 2000. But this is one way to define a sequence. Does it look like a collection? You collect number 1, and then you collect number 0, and third time you collect number 1 again, right? And then so on. That's one example of a collection. So second example of a collection is kind of opposite rule, and here 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, and dot, dot, dot. Is that kind of the same pattern? Right? It's just that the role of 0 and 1 is switched. So you understand dot, dot, dot? Right? What is A6 then? Is that supposed to be 0 this time? Yeah. You can count it. I hope it's right. So I'm guessing it A6 is 0, and so on. So this is a way of a sequence. You write down dot, dot, dot. But soon you understand the concept, you quickly switch to this type of definition. AN given by a formula like this, n divided by n squared plus 1, where n is 1, 2, and 3, and dot, dot, dot. So the first number you're collecting will be what? What's the first number? N equals 1. You plug it in there. So it's 1 divided by 1 squared plus 1. 1/2. Right? That's our first number. That's what I mean by this sequence. How about A5? Can you calculate A5 in this case? 5 up there. And 26 in the denominator. Is that right? 26. All right. You can't reduce this one. So that's the fifth term if you list those numbers. That's what I mean by sequence. And you dealt with that in calculus 2 a lot. So that's a sequence. So rather than defining what a set is, I'm just going to create a set using these 3 sequences. All right? All right. So I was trying to say earlier that defining a set is tricky. So just use this example. So let's generate a set. Arrow means that out of this sequence, I'm going to generate sets. Principle of a generating set here, I'm going to use this term abstract. But right down here, sets are abstract. If you already know what sets are, then you might get puzzled by what do you mean sets are abstract? That's just very concrete. You dealt with it a lot in my proof course. But here's why I'm looking at this as an abstract object. Can you recognize this A is somewhat representing the very first sequence? I'm going to go ahead and erase this name and change the distinguish everything to something that's like B and C. Is that okay? So first sequence is called AN, second sequence is called BN, third sequence is called the CN. Okay? A represent the first sequence. It's not a set. It's a sequence that I described. Collection of number with order, right? And you can see a lot of repeats in this number, in this sequence, right? The B is, maybe it's representing the sequence Bn, okay? And then you forget about what I just said. This A and B is going to be sets generated from this sequence, An and Bn, by ignoring the repeats and order. That's the key in the sense. So repeats, what do I mean by repeats in the sequence? 0 is repeated a lot, 1 is repeated a lot. So ignore that. 0 is there, 1 is there. Doesn't matter how many times it's repeated. And it definitely has order. 1 comes first, and second term in that sequence is 0. Totally ignore the order. So 1 is in there, 0 is in there. They're repeated many times with a certain order, but repeat and order is ignored. So what kind of information is carried in here, in A and B? It's called a membership. So I'm going to write down the membership. It's 0, a member of A. What do you say? The capital A represent the first sequence An. Is 0 in there? It's in there, right? Is 1 in there? 1 is in there. That kind of question is called a membership. So 0 is in there, 1 is in there. It has this order and it repeats a lot. Just ignore that part. Just questioning, is 0 in there and 1 in there? How about B? Is 0 there? 1 is there. Is there A and B in that sequences? Is there anything else in there? 0 and 1 is the only thing that is in there, right? Both of them. So set only recognizes this property, the membership. Because of that, they have exactly the same membership. We write these two sets are equal to each other. But this sequence An, sequence Bn, are they equal to each other as a sequence? Sequence is sensitive about the order and repeats, exactly the way it's lined up. They're not the same, right? Sequence is not the same. But set that's generated out of the sequence by ignoring the order and repeats, just keeping the membership information, and they're exactly the same object in there. Okay? That's one. So the reason I call this an abstract is the following. Here's one apple, and here's another apple. In reality, they're called apples, but it's different. Its weight's different, shape's different, the coloring is different, right? It's like a sequence. The chemical structure and physical status is different, but they're the same. They're apples. Only caring about certain common properties, right? That's what we're doing. We're looking at very sensitive objects called sequences, but just focus on one information. What is that one information called? Membership. They have exactly the same membership. Then this abstract notion called sets is equal. But what is really concrete object we're familiar with, we feel comfortable with, is the sequences. Make sense? Okay. So how about this comment now? It's kind of abstract. The actual object you've been dealing with, or familiar with, is not really the sets, right? Yeah. But sets is some abstract notion out of it. And so how many members are there? 2 members, right? Because there are only 2 members, we call it a finite set. But what about the sequence An? Is that a finite sequence? An goes on forever because of the ... information I gave you, right? The sequence is infinite, but the set correspond to that sequences that I stated there is finite. Right. So can somebody come up with an interesting question about the finite set and infinite set, those two things that are introduced in here, by looking at this example? What example? A and B and C and example here. Is it easy to answer the question, is the set generated by the sequence a finite or infinite? It's easy for an because we know what this dot 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 means, right? 0 and 1, two members. Finite set or infinite set? An as a set. Finite set, two members. Bn, finite set or infinite set? Finite set, only two members are there. Cn, what's your gut feeling telling you? There's a What is the question that you have to ask? It was obvious from the 0 and 1. There's no question. It's evident. No proof is required. But Cn, if you want to write down an absolute, rigorous mathematical statement that's not relying on your feeling, or what is that you have to prove? As you plug in n equals 1, n equals 2, and n equals 3, you have to explain this number will never repeat again. Just keep giving me a new number, right? You can verify by plugging n1 through 2014, whatever the computer can handle. That doesn't prove it's infinite, right? You have to just keep trying, pass it on to your daughters and ask them to keep trying and see if that repeats. That's not going to do the business, right? You have to mathematically argue. For sure, with absolute certainty, this will never repeat. Eventually, it's going to keep spitting out new number and new number and new number. From there, you can conclude this is an infinite set, right? Because repeat will never be there. It's new number to spit out as you plug in n equals 1. That's what you have to establish to say that. So that was the example I wanted to go through. At all. Now it's going here, but I'll get used to it later on. But you have this note. What is the difference between circle and disk? These are sets of. The circle is a set of something, and disk is a set of something, right? The set of circle is a set of position, and here, and disk is a set of position. Everything. Okay, basketball rim versus actual silver disk. That object is the difference between circle and the disk. So when we recognize in mathematics, when we say it's a circle, we're just talking about that rim in there, right? Is that point in there contained in that set A? That means that point we're looking at it here is as a set is inside that A here. No, it's not on that circle, right? So contained doesn't mean that it's bounded within something. It contained in strict sense like this. Member is a member of another one. But mathematicians use this term, contained in. Okay? When you read books in this level, they just use this language, sometimes not explain too much, and then students get often confused with this type of terminology. If A is contained in B and B is contained in A, and what kind of corollary do you get there? Can somebody write down simple corollary out of these two? I give you 3 definitions. Is that right? Did I give you 3 definitions? A is equal to B, A is contained in B, B is contained in A. Right? So A is contained in B, and B is contained in A. Every member is in back and forth. If we have this condition, what do you guarantee? What do you guarantee about relationship between A and B? These two things are satisfied, right? Therefore, they must be the same sets. Yeah. Sounds reasonable? Then you have to go a little bit beyond. It's not reasonable, it's absolutely right. Right? A is equal to B. If A is equal to B, do you think you can guarantee that A is always contained in B, B is always contained in all the members in A is in B, all the members in B is going to be in A? Do you guarantee that? That's the very definition of this two sets being equal to each other. So this type of statement is called equivalence statement, right? So it's a shorthand for basically something that's written in quantified expression. These are called quantifier. recording now. Notation. Is that fair to say that I've so far introduced, using example, notion of set, not the definition of sets, just concept of a set, and I introduced the definition of set being equal to each other and one set being contained in another set. Fair to say? This is a notation now. We already have some notation up there. 1 0 1 0 1 0 and 0 1 are sets. So these are the notation for the sets. But it looks a lot like sequences, right? Seems like I wrote down two sequences and put these curly braces around it, right? So here's a sequence without curly brace. If you put the curly brace around it, what does it become? Becomes a set. Notation, a list of number with separated by comma. You put the parentheses, it becomes a set. Does the sentence make sense? These two things are not sets. But let's apply the definition we just learned. What kind of relationship do we have about these two sets? Move around here. These two sets are contained each other or equal to each other? What do you say? Two sets are equal to each other. It's only about the membership, right? Yeah, only about the membership. What members do you see in the left first set? 0 and 1, those are the only members show up. However repeated in what order doesn't matter. What about the second set? 0 and 1. So since these are sets now, I can write down, okay, this set that is stated like this, and that set stated like that. And what is the symbol that goes here? Equal. Equal. That's the symbol. Does that make sense? It's all about the membership. So you might get puzzled by the following question. Let's prove it. You all agree that that's obvious. That's equal to, let's prove it. So here's the prove it. My phone's ringing. I have a death in the family recently, yesterday, my wife and... All right. So I'm going to write down, let's prove it, and here's a proof. This is about just going through the definition. Maybe very first kind of proof you're encountering in this course. So that we're going to state it like this, and A, maybe going to write it, let A be that set, 1 0 1 1 0, and name that set B 0 and 1, like that, right? Is it expressed in a different way? And usually, let's say it's item number 1, and let's prove A is contained in B. Okay? I didn't prove it. I'm about to prove it. And maybe I'm going to write it like this. There are how many members in there? Like 5, not members, there's 5 entries, right? 5 entries in what set? A. So we can count them all, and there are only how many members? Only 2 members. How about that? Okay? You can imagine that it's described in a different way. You can't just go through one at a time. That's not going to be a good proof, right, if there's infinitely many of them. But because there are only 5 entries, we can go through each of them, write down absolutely correct statement. We went through 5 items, only did the 2 different items, the 2, so two members are there. So those two members are what? Two members, 0 and 1. Correct? All right. So let me go back to this definition in here. You have to establish this one. Whenever you pick an element from A, you have to show that element is in the B. That's what we're about to do. How many elements are there in A? How many members are there? 5 or 2? Only 2 members are there, right? So whenever here is simple, for those 2 elements, that's all you have to check. Okay? It's quite visible. You see everything is going on here so that you don't see the need of going through this detail. But whenever sets in the disguised form, this step is very important. So you have to take that perspective there. So whenever X is coming members of A, and this part is taken care of, 0 is a member of A, and 1 is a member of A. By the way, that I didn't explain the symbol. I'm going to write it big here. This symbol belongs to or is a member of the following set. X is a member of set A. They use the symbol here as a shorthand. Okay? So whenever is equivalent in this case, 0 is a member of A, 1 is a member of A. That's all we have, right? So we have to establish, okay, when 0 is a member of A, is 0 a member of B? Well, 0 appeared in that B, so this is true. What about 1? 1 is a member of A, and 1 is there still in the B, therefore 1 is a member of B. So I strictly went through that statement. Whenever X is an arbitrary member of A, I established the fact that it's also a member of B. Effective way of proving when you're dealing with very small sets like this. The best way to prove it. But if it is really like it contains like 2,000 some elements and you don't see the pattern, and checking one at a time would take a lot of time. Maybe you have a description just like that, n divided by n squared plus 1. Then you don't want to deal with this one at a time. You want to deal with the formulas and show different ways, right? But it has to follow this structure. With this baby example, I went through that structure. So what did we prove so far? We proved that A is contained in B. Did we prove that? All the members of A is all the members of B. We have established that. Good? So what is the next statement to prove? Yeah, we're going to prove B is a member of A. We're going to do that. All right? So would you like to go through this structure on your own? Let's spend probably 3 minutes. I bet you can imitate this thing and produce your proof. I'll write down my answers here, but you can work on yours. From that, we established A is contained in B and B is contained in A. That's the same as establishing these two statements there. Therefore, we conclude out of that right there, because of these two statements, you write that therefore A is equal to B. And that's the end of the proof. You know this symbol? Have you seen this symbol like a box in here that indicate that no matter you understood it or not, that's the end of the proof. That's the symbol right there. Why do they need a symbol? Because it lets you know that you probably didn't understand, but that's the end. That's why the symbol is there. Anyway, they use that symbol. And I had to think about why do they need a symbol in there? Because they think proof is hard. All right, so that's the typical thing. So I said that this is the proof using the definition. Does that make sense? It's not using some big theorem or a clever idea. We went through the very definition of a two set being equal to each other. Went through each statement by statement. Brute force proof, that's what you call it. But very inconvenient often, but it shows us a clear idea about this concept. That's what the definition is. And then we work on better theorem, so you don't have to go through checking all the time. So some sort of theorem that takes care of this checking procedure, and cleverly we can just say that two sets are equal to each other, things like that. All right? So whenever you see use the definition to prove that, and you have to do the labor of going through each statement. I will phrase it that way. Okay. This is about time 3:06. The class is supposed to end at 3:15, right? And I already missed that discussion time. The quiz I have prepared is a little bit containing a little bit more than this, so I'm not going to do that quiz problem. But let me just introduce what's in the next part. But since I don't see right now any discussion item, I think I explained very thoroughly. So we're about to wrap up, and this one here, and I mentioned something called infinite set and finite set. Those little a(n) and little bn, those were infinite set or finite set as sets. They're finite set. They only have finitely many members, right? But Cn we didn't know. The question was a finite set and infinite set. The answer is infinite set, and you need to prove it. Okay? All right, that would be a set 2 problem because it requires a little bit of trig, and we really have to come up with a nice method of arguing that is infinite. Typical set 2 problem is going to come like this. If you like it, you work on that. If not, you don't have to, but there will be specified. This is so hard, I'm going to give you 5 points. Or not so hard, I'm going to give you 2 points. It will have awards there stated next to the problem. All right, that's roughly about it. So let me introduce just one more notation, and that'll be it for today. This is called a black boldface Z. That's capital Z, but you see that, double line there? That's boldface Z. This is a set of all integers. You know integers? 0, 1, and -1, and 2 and -2, those things. Boldface Q, like this. These are rational numbers. Anybody know this convention? What is the next level? Real numbers? They're writing as boldface R like this. It's real numbers. Complex numbers, it's denoted by C. I think this first two came from German. I don't know, my guess. What is the next level of numbers? Complex numbers are pretty much it, right? That's the pretty much universal domain. Next thing is that this is a set of real numbers, right? And this represents xy plane. The position in xy plane requires 2 real numbers, right? So they denote it like this. And how do you represent the position in xy plane? Using the tuple, right? So for example, 2.5 comma √3. Does it look like a position in xy plane? Right. Is this a member of what set? R2, right? This is a member of which set? R2. So R2 is just a notation for entire xy plane. As what? Set. Plane has a whole lot more structure. What is right next to it? It's a whole geometric object, and set is not. Set only cares about whether it has that member or not. So when we say plane, it's like actual apple, a lot more sophisticated structure in it. When we say xy plane as a set, it's a very dull object, right? It's just a membership information. That's what that is. So when we write it like this. If you really want to represent it in mathematics, with all the structure, 1 comma 1 is close to 0 comma 0 than 5 comma 5. That kind of information, they use Euclidean space. It's like this. So this is not just a set, this is actually have a structure and things like that. So as I said, these two things are the same, but this emphasizes more of a geometric structure. How about R3? What would you say about R3? XYZ plane, not a space. But this is not really space, right? This is just a set. Ignore all the structures you have in the XYZ plane, just a collection of position. And you can put this exponent everywhere. You can get some extra sets created out of this. All right? So what's a good title of today's lecture? Sets. What are sets? When they're, what do we mean by the sets are equal to each other? Do you agree sets are a little bit abstract notion compared to sequence, right? That kind of thing. All right, that's it. I'll end it here. No quiz today.